Hello children, in previous video we have learned about wave nature of electromagnetic radiation. In this video we will talk about particle nature of electromagnetic radiation. First we will see two phenomena related to waves and they are diffraction and interference. Then we will see two phenomena related to particles and they are blackbody radiation and photoelectric effect. Diffraction. Diffraction is the bending of wave around an obstacle. Suppose this is obstacle and this is approaching wave. After hitting the obstacle, this is bent wave. So this phenomena is called as diffraction. Interference. Interference is the combination of two waves of same or different frequencies to give a wave whose distribution at each point in space is the algebraic or vector sum of disturbances at that point resulting from each interfering wave. To understand it clearly, we will consider two cases. In case 1, wave 1 and wave 2 are identical waves. At any point on x-axis, y magnitude of resulting wave will be double of any of the waves. In case 2, y magnitude of both the waves are same, but they are opposite in direction. So, y magnitude of resulting wave will be 0 at any point on x-axis. Now let us talk about blackbody radiation. Max Planck in 1900 explained blackbody radiation phenomena. Suppose an iron rod is getting heated in a furnace. As its temperature keeps on rising, its color keeps on changing. First it becomes dull red, then more and more red, then white, and finally blue. What it means is red radiation is intense at a particular temperature and blue radiation is intense at a particular higher temperature. So we can conclude that intensities of radiations of different wavelengths emitted by hot body depend on its temperature. Also, objects made of different material and kept at different temperatures emit different amount of radiation. When the light falls on the surface of an object, a part of radiant energy gets reflected as such, a part gets absorbed and a part gets transmitted. Absorption is never 100% as ordinary objects are imperfect absorbers of radiation. Black body is an imaginary object which is supposed to absorb and emit radiations of all frequencies uniformly. A close approximation of black body can be carbon black. Another close approximation of black body can be a cavity with a tiny hole. Suppose this is a cavity and this is a tiny hole. There is no other hole in the cavity. Light enters from this tiny hole but doesn't find way out. It keeps on hitting the inner wall and keeps on getting reflected, ultimately losing all its energy and gets absorbed by the cavity. So this cavity can be called as a black body. A black body is not just the perfect absorber, it is perfect radiator of radiant energy. That means at any given point of time, it is in thermal equilibrium with its surroundings. It radiates the same amount of energy per unit area as it absorbs from its surroundings. Intensity of radiation from a black body and its spectral distribution depends only on its temperature. At a given temperature, intensity increases with increase in wavelength, reaches a maximum value at a particular wavelength, and then starts decreasing with increase in wavelength. Also, when the temperature rises, maxima of the curve shifts towards shorter wavelength. Scientists tried to find out relation between intensity and wavelength, but they could not get any convincing explanation based on wave theory of light. Then came Max Planck with his assumptions. Planck assumed that absorption and emission of radiation arises from oscillator, that is, atoms in the wall of black body. Their frequency of oscillation is changed by interaction with oscillators of electromagnetic radiation. Recall our example of a cavity with a tiny hole in which electromagnetic radiation enters but doesn't find a way out. It keeps on hitting the inner wall of the cavity. So at every collision, frequency of oscillation of these atoms gets changed by oscillations of this electromagnetic wave. That is what is written here. Since the emission or absorption happens only when the collision occurs, So Planck assumed that radiation could be subdivided into discrete chunks of energy. He suggested that atoms and molecules could emit or absorb energy only in discrete quantities and not in a continuous manner. He gave the name quantum to the smallest quantity of energy that can be emitted or absorbed in the form of electromagnetic radiation. The energy E of a quantum of radiation is proportional to its frequency nu and is expressed by E is equal to h nu, where h is Planck's constant. Its value is 6.626 into 10 to power minus 34 joule second. E can take values 0, h nu, 2 h nu, 3 h nu, etc. That means 0 or positive multiplier of h nu. So general formula is E is equal to n h nu, where n is 0, 1, 2, 3 and so on. Now let us talk about photoelectric effect. In 1887, a scientist named Heinrich Hertz performed an experiment in which electrons were ejected when certain metals were exposed to a beam of light. This phenomena is called as photoelectric effect. He observed three things. First, electrons were ejected as soon as the beam of light strikes the metal surface. That is, there is no time lag between the light striking the metal surface and ejection of electrons. Second point, number of electrons ejected is proportional to the intensity or brightness of the incident light. Third point, for each metal there is a characteristic minimum frequency nu0, also known as threshold frequency, below which photoelectric effect is not observed. If the frequency is more than nu0, then electrons come out with certain kinetic energy. If frequency is increased further, kinetic energy of these ejected electrons also increase. The experimental results were a bit unexpected. As per classical physics, the number of ejected electrons and the kinetic energy of ejected electrons should be dependent on brightness of incident light. The experimental results suggested that though the number of ejected electrons depends on brightness of incident light, kinetic energy of ejected electrons does not. Rather, it depends on frequency of incident light. Einstein explained photoelectric effect quite convincingly using Planck's quantum theory of electromagnetic radiation. He said that when a photon having sufficiently high energy strikes an electron in the atom of the metal, it instantaneously transfers its energy to the electron, causing its ejection. Greater is the energy of photon, greater is the transfer of energy, and greater is the kinetic energy of ejected electron. If striking photon has energy h nu and the minimum energy required to eject the electron is h nu 0, then difference of energy h nu minus h nu 0 is transferred as the kinetic energy of photoelectron. So h nu minus h nu 0 is equal to half mv square, which is kinetic energy of ejected photoelectron. So we can say h nu is equal to h nu 0 plus half mv square. Here h nu 0 is called as work function. Now let us see few numericals based on photoelectric effect. First question, calculate energy of 1 mole of photons of radiation whose frequency is 5 into 10 to power 14 Hertz. Energy of one photon is given by h nu, where h is Planck's constant. Its value is 6.626 into 10 to power minus 34 joule second. Frequency nu is given as 5 into 10 to power 14 Hertz. So energy of one photon comes out to be 3.313 into 10 to power minus 19 joule. Energy of one mole of photons will be energy of one photon into Avogadro number. And we know that Avogadro number is 6.023 into 10 to the power 23. So energy of one mole of photons comes out to be 1.995 into 10 to the power 5 joule. Second question, a 100-watt bulb emits monochromatic light of wavelength 400 nanometer. Calculate the number of photons emitted per second by the bulb. Wavelength lambda is given as 400 nanometer. 1 nanometer is equal to 10 to the power minus 9 meter. So lambda is equal to 400 into 10 to the power minus 9 meter. Power is given as 100 watt. That means 100 joules per second. Energy of one photon is given by h nu, where h is Planck's constant. Nu is equal to c by lambda. Value of Planck's constant is 6.626 into 10 to power minus 34 joule second. C is speed of light. It is 3 into 10 to power 8 meter per second. Lambda is 400 into 10 to power minus 9 meter. So energy of one photon comes out to be 4.97 into 10 to power minus 19 joule. Number of photons emitted per second is given by power upon energy of one photon. Power is 100 joule per second. Energy of one photon is 4.97 into 10 to power minus 19 joule. So it comes out to be 2.012 into 10 to power 20. Third question, when electromagnetic radiation of wavelength 300 nanometer falls on the surface of sodium, electrons are emitted with a kinetic energy of 1.68 into 10 to power 5 joule per mole. What is the minimum energy needed to remove an electron from sodium? What is maximum wavelength that will cause a photoelectron to be emitted? We know that energy of one photon is given by the formula E is equal to h nu. Nu is equal to C by lambda. So E is equal to hc by lambda, where h is Planck's constant and C is speed of light. Value of h is equal to 6.626 into 10 to power minus 34 joule second. Value of C is equal to 3 into 10 to power 8 meter per second. Lambda is given as 300 nanometer, which is equal to 300 into 10 to power minus 9 meter. So energy of one photon will be equal to 6.626 into 10 to power minus 19 joule. Energy of one mole of photons will be equal to energy of one photon into Avogadro number, which is equal to 6.023 into 10 to power 23. So energy of one mole of photons is equal to 3.99 into 10 to power 5 joule. Minimum energy needed to remove 1 mole of electrons from sodium will be equal to energy of 1 mole of photons minus kinetic energy of electrons. So that comes out to be equal to 2.31 into 10 to power 5 joule. Minimum energy for 1 electron will be equal to minimum energy needed to remove 1 mole of electrons from sodium divided by Avogadro number. So that comes out to be 3.84 into 10 to power minus 19 joule. Corresponding wavelength we can calculate by this formula, lambda is equal to hc by E. Value of E is this. So lambda comes out to be 517.7 nanometer. Fourth question, the threshold frequency nu 0 for a metal is 7 into 10 to power 14 per second. Calculate the kinetic energy of an electron emitted when radiation of frequency nu is equal to 1.0 into 10 to power 15 per second hits the metal. We know that kinetic energy of an electron is given by the formula half MeV square, where m is mass of electron and v is velocity of electron, and that is equal to h nu minus nu 0. So kinetic energy is equal to h nu minus nu 0, where h is Planck's constant. Its value is 6.626 into 10 to power minus 34 joule second. Nu is given as 1.0 into 10 to power 15 per second. Nu 0 is given as 7 into 10 to power 14 per second. So kinetic energy comes out to be 1.988 into 10 to power minus 19 joule. In next video, we will talk about spectrum and Bohr's atomic model. If you have a question, you can ask me on my Discord server. If you have not subscribed my channel yet, please do so.